small q k, right? We can write in this way, or we can use this group theory notation writing this way in single column. This means all these three quarks are antisymmetric with respect to each other in the color space. And then if you write in a more transparent way using epsilon ijk, and then it's written in this way, okay? But you see these two guys. So the upper, these two blocks, this corresponds to 3 bar. But this guy corresponds to 6. So now if you put one additional quark to this one, you cannot form a single column, right? You can only form either here or here, but it's not possible to get a single column. That's why this 6 and this 3, they cannot form color singlet. But this 3 bar is already here. You have these two in the single column. You just put another one here. You get a singlet. Okay. But this is a very good question, because this makes a difference if your doubly heavy hadron does not have a single light quark inside. For instance, if you have 2 light quarks, and then things becomes different. Any more questions? Okay, then let's come to these kind of examples. I show you what kind of conclusion that you can simply make by the very simple consideration that I talked about, and also talk about by Juan for the chiral symmetry simultaneously breaking. So this one was observed by the D0 collaboration. D0 collaboration in 2017, probably 17 or 16, around this year. Okay. So this was observed in B sub s pi, observed in B sub s pi, okay? Pi plus, pi minus, okay? And it's observed as a very clear peak. But then, of course, this looks like very exciting. You see a very clear peak in B sub s pi plus, right? B sub s, that's B bar s. For instance, if you consider the pi plus, and then you would have U d bar. If this really exists, and then you would have already observed a really exotic tetraquark state with 4 different quarks. That would be fantastic. But the question, of course, is whether this observation, or how to interpret this observation, whether you think this observation, whether you trust this or not, so to say. But the first observation that you can see, the first point that you can make is that is this guy, the mass is 5568 MeV. Okay, you know, what is the mass of the B sub s? Do you remember? I also cannot remember. but we know the approximate value. I know the B mass is 5.27 GeV. B sub s mass is approximately 100 MeV higher. So the B sub s mass would be around 5.37 or so, right? Around this value. And then you see this one. The mass of this X, 5568, minus the mass of B sub s is only 200 MeV. Would you think this weird? Or you think that's reasonable? You see, B sub s, that's B bar s, right? And this one now you have 2 more quarks, or 1 more pair of quark antiquark, right? You have 1 more UD bar pairs. But their mass difference is only 200 MeV. So you think of all your knowledge in hadron physics. Where can you find any other single example that if you have 2 more quarks and the mass difference is only 200 MeV? You cannot find any, right? Because normally, if you just simply qualitative understanding, if you simply add one more quark, and your mass will increase by the order of lambda QCD, which is 200, 300, 400 MeV, depending on how many flavors you consider. And then if you add one pair of quark anti-quark, and then your mass would increase by 2 times the lambda QCD, right? At least 500, 600 MeV. But this one, the difference is only 200 MeV. Okay? The only single example that you can think that has a mass of around 200 MeV with a pair of quark anti-quark is a pion mass, right? Okay, I already write this down. I just wanted to ask whether you know this pi mass. This is 140 MeV, right? It's around 200 MeV. But we already learned from last lecture, there is a reason for this. What is the reason? Very special one. Yes, that is because this is the pion is a pseudo Nambu-Gaussian boson of the spontaneous breaking of chiral symmetry. If the QCD Lagrangian has an exact chiral symmetry, and this pion would be exactly massless, right? But of course, the up and down quarks, they have a little bit of mass. The up quark mass is around 2, 3 MeV. The down quark mass is around 4, 5 MeV in MS bar scheme, to Jeff scale. And then, this very little mass of the quarks, the light quarks, introduces a very small mass for the pion. But other than that, you cannot find any other single hadrons with such a small mass by introducing one additional pair of quark anti-quark. Right? So from chiral symmetry, this kind of consideration. We would conclude, point 2, Jeff, because here you can hardly think there is a kind of chiral symmetry breaking plays a role in just adding 200 MeV to this B sub S ground state meson. One would think that the mass of B bar S U bar D or U D bar, this kind of Terracock state would be at least M B sub S plus 2 lambda QCD, right? Of course, there is one way. There could be one way that chiral symmetry spontaneous breaking play a role. That's because that would be, for instance, you can ask that your pion interacts with this B sub S, right? Because your pion is very light. The pion is a pseudo Nambu-Gaussian boson. In case your pion interacts very strongly with B sub S, and then in principle, it can produce some kind of state with a mass just 200 MeV above B sub S, right? So exception. Pion interacts strongly or attracts strongly. With B sub S. And then they can produce some state from this kind of interaction. But can this happen, right? And the question is whether it's possible to have this kind of scenario realized. But we immediately see this is very unlikely. That is because your B sub S is B bar S, right? That's your B sub S. But your pion, pi plus, for instance, is U D bar, right? They don't have any common quark flavor. No common quark flavors, right? They don't share any quark flavor. And then this kind of interaction, there is a name in hadron physics. It's called OZI suppressed. Because you can draw a single line, you can cut all these quark lines into two separate color singlet blocks. Okay, this interaction is OZI suppressed. OZI means Kubo Zweig Izuka suppressed. And then this kind of suppression means the quark line diagram can be separated into color singlets, groups. Okay, by drawing some line, right? Here you see for sure this can be separated because the above one is color singlet group. This one is also color singlet. So this is OZI suppressed. And then this means the interaction is pretty weak. Although this OZI suppression is a phenomenon that was observed or well satisfied by the hadron physics phenomenology, there's one kind of explanation of this, which please. That's right. You can think in that way. Yes, you can. Or you can have Gluon exchanges, for instance, which I do not draw. Okay. Very good. There's one possible explanation of this. This is using the brilliant idea to change the number of colors. Okay, you will find, which I will not go into details, but you will find this kind of OZI suppressed scattering is relatively suppressed by 1 over NC compared to the ones that are allowed by OZI rule. Okay, relatively suppressed. Relatively suppressed. But although this 1 over NC is not very, it's not a very small number, but we see in many cases in hadron physics, the OZI rule is satisfied very, very well. For instance, you find this phi, for instance, right? What is the dominant decay channel for phi? Phi decays to what? Pion? Actually, the dominant decay channel, of course, it can decay into pions, 2 pions, for instance, but that's not the dominant ones. And that's, this decays almost 100% into KK bar. Of course, your question would be why this phi could not decay into for instance, rho plus pi. And that was the question that Zweig asked when he proposed his version of quark model. Right? He just wanted to answer that question, and then he found his version of quark model from this very specific question. And of course, this is why we have this Zweig rule. So this basically this SS bar, this phi, this SS bar, and then you have KK bar, right? So this is allowed by propagating S and S bar to the final state, and at some point you create a pair of, for instance, U bar U or D bar D, and then you create this KK bar, right? And then this is allowed by OZI rule because you cannot draw a single line to separate all these quark lines into 2 separate color singlet groups. It's not possible. But on the other hand, if your final states are, for instance, pi pi or rho pi, well, one question is phi to pi pi, whether this can happen. If not, or if yes, whether this is suppressed in addition to this to the OZI suppression. You can think about this. So there could be also one exercise that you think of pi-pi pair, whether this couples to phi, and if yes, what would the or in what kind of a symmetric limit this should not happen, and in what kind of situation this can happen. Right? But then I will simply put rho and pi. Okay? And then this is S bar. You have S bar, but for rho pi, you have U bar, D bar. Right? You have U bar, D bar D, for instance. And then they don't share the same common quark flavors. The only possible interaction would be their analysis into gluons, and then the gluons they hadronize into the final state rho and pi. Some hint, you think of the G parity that I talked in the yesterday. I didn't write here, but maybe for the review I can just put more pieces. So the parity for quark anti-quark pair is -1 to the power of L plus 1, right? For this C parity, what is C parity? Do you still remember? -1 to what power? For quark anti-quark, yes. For QQ bar, for instance. Yeah, please. Okay, please. Yes, L plus S, right? This L is the orbital angular momentum. S is the total spin of the quark anti-quark pair, and then this only holds for flavor neutral hadrons, right? For flavor neutral meson, and then we have this G parity. What is G parity? -1 to what? Who still remember? So you remember the G parity, how this is introduced, right? We make two different transformations. First transformation is we make a C parity charge conjugation, and then in order to have your, we give some example, pi plus, pi minus here. We make C parity transformation, and then your pi plus becomes pi minus, your pi minus becomes pi plus. And then in order for these states to be eigenstates of this new introduced G quantum number, we need to make some rotation. This is I, Y, the isospin space. Make a rotation around, of 180 degrees along the y-axis, the IY axis, right? And then this introduces -1 to the power I times the charge conjugation, the C parity, right? In total, you have -1 to the power L plus S plus I. Okay. So if you understand this picture, and then you don't really need to remember this, to memorize this. You just know this is basically the C parity times -1 to the power I. Okay. And then use this, you can make judgment of whether phi decays into pi, or in what kind of limit it cannot. So, let me go back to the B sub S pi instruction. This means in the B sub S pi, their instruction must be very weak. Okay, B sub S pi must instruct weakly. Okay, because they are always suppressed. Of course, there are some other OZI suppression, OZI rule very respecting hadron physics. For instance, the deep psi mass is 3.1 Jeff, but its width is only 100 keV. Right? Although it has plenty of phase space to decay into many pions, but its decayivity is very small. So this means it's basically from this kind of consideration, it's not possible to have a tetraquark state with a mass just 200 MeV above B sub s mass. Okay? That's one consideration. The second consideration would be heavy quark. We can use heavy quark flavor symmetry, right? If there is indeed this kind of tetraquark state, existence of B bar S U D bar tetraquark state, tetraquarks would immediately lead you to prediction of their or its charm partners. Okay. You simply replace your bottom quark or anti-bottom quark by the anti-charm quark, right? And then your anti-charm CS UD bar tetraquark state, the mass would be approximately this B bar S UD bar minus the mass difference between bottom and charm quark masses. Right. Which is 4.5 minus 1.5 is around 3 Jeff. You simply subtract 3 point something Jeff from here. So if you, for instance, if you use the B sub s mass and D sub s mass to estimate this mass difference, B sub s mass, as I just said, is around 5.37, and D sub c mass is how much? 1.968. It's around this value, right? GeV. And then you get around 3.4 Jeff. Around 3.4 Jeff. And then you subtract this away. You would be able to estimate the mass for this kind of a tetraquark would be around 2.2 Jeff, right? Plus minus, for instance, 150 MeV difference uncertainty for using this heavy quark flavor symmetry. And this is also being one state. And then this should be able to decay into D sub s pi. And then you just look at all this data existing, you find nothing. But in principle, this D sub s pi should be much more easily be produced than the B sub s pi, right? Because your charm quark is much lighter than your bottom quark, and then its production is much less suppressed in heavy in any collisions. Which one? Yeah, well, here I have not. I did not talk about the meson-meson structure. Here, what I mean is that if we assume the existence of this kind of a tetraquark, no matter what kind of internal structure it has, right? No matter what internal structure it has, it must have a charm partner. Doesn't really matter what this is. It must have a charm partner, because this happens just by replacing the bottom quark by charm quark. And we have already said that there is a heavy quark flavor symmetry, right? Heavy quark flavor symmetry. So you simply replace your bottom quark by charm quark, and then all the remaining non-perturbative KCD dynamics remains almost the same up to corrections of order lambda KCD over MC minus lambda KCD over MB, because you move from bottom sector to charm sector. Okay. So any more questions? So this, if you observe these 2 points, this would encourage you to question the observation, right? And indeed, on several experiments, they tried to reproduce this D0 observation, and all of them filled. And this include CDF, which is located in the same lab as D0, right, as Fermilab, and RCB, and the CMS, and Atlas. They all failed to find a positive signal for this B sub S 5568. But if you think in terms of these very simple theory arguments, you would already questioned the existence from the very beginning. Right? Yeah. But then this is this argument. So you would hardly think of any arguments that suppose you that you have one more pair of quark anti-quark, but you have only a 200 mass difference. But yeah, it does not matter. I didn't specify any internal structure, any kind of picture for this kind of state, right? The only argument that I used is that 200 MeV is too small for creation of a quark anti-quark pair. No. Then I said. With this I wanted to see there could be kind of an exception. The exception would be the pion. That if this pion interacts very strongly with B sub S, because the pion has a very light mass, around 200 MeV, 140 MeV. But there is very good reason for the pion to have that light mass, because it's a pseudo Namba-Gusson boson. And then we want to see whether this kind of picture can give you some reason to believe it's possible to have 200 MeV just by introducing one more pair light anti-quark, light anti-light quarks. But from this kind of analysis of the OZI rule, it turns out it's very unlikely. And then again, this would be that would lead you to ask, how is that possible to have a such huge body energy, right? Huge body energy would means you have very strong interaction, and then this gives you kind of introducing one pair of quark anti-quark pair with a mass of 200 MeV. This would be very similar to the creation of pion. But there we have a very special reason because of chiral spontaneous symmetry breaking. But here, one can hardly see a similar reason to have that very huge body energy. Okay. Yeah, I know that there are many papers discussing this. If I offended any of you, I apologize for that. But this is this would be a qualitative understanding from considering these basic ingredients. Right? So that's one example. On the next one, okay. Actually, I think it's also the right place to explain some qualitative estimates of isospin breaking, because this one was observed in B sub S pi, right? And the mass is the width is around 20 MeV. But from here, we would already conclude this one, if this exists, is isospin vector states. Because otherwise, if this is isoscalar, then isoscalar couples to B sub S pi, that would be isospin breaking. But the question is how large isospin symmetry breaking should be. How large is the isospin on symmetry breaking? So these are all qualitative dimensional analysis. Okay? And then to answer this question, then this requires us to understand the origins of isospin symmetry breaking. What would be able to cause isospin symmetry breaking? What's the source, or what are the sources for isospin symmetry breaking? What is isospin symmetry? Very good. Up and down quark masses are not the same. Is there other reason? Yes. The charge of the up and down quarks, they are not the same, right? We have two different reasons, because isospin symmetry lists up and down quarks, and then they have different masses, they have different electric charges. So this one normally called QCD source for isospin breaking. This one is normally called QED source for isospin breaking, or sometimes called virtual photon, virtual photons, okay? Because the photons they are exchanged in terms of inside this hadrons, they must be virtual, okay? But this is virtual photon. This means this must has kind of at least exchange one photon, but then a single photon gives you some suppression factor of alpha, right? Which is 1 over 137, which is 10 to minus 2, right? For this one, for the QCD source of isospin breaking, this is at the amplitude level. At the amplitude level, right? For QCD, and then that would be order of MD minus MU, or divided by something, right? Because this is a dimension-4 quantity. It should be divided by some other quantity having the same dimension, but that one should be respected by isospin symmetry. And what that should be, and then that is normally lambda QCD or MS, this kind of stuff. Because if your system is isospin conserving, and then the dynamic is simply governed by the non-turbulent QCD, and then the normal energy scale would be lambda QCD. Or in some cases, for instance, in pion eta mixing, what happens would be there is a pion mass, sorry, not pion mass, a strange quark mass, because there the light quark masses enter. But again, these are the order of 10 to minus 2, right? So that's at the amplitude level. And then at the, for instance, in the decay width level, for the isospin breaking, compared to isospin conserved, the ratio would be something around 10 to minus 4, 10 to minus 3, this kind of region, right? Because you simply squared this kind of estimates. And then the normal width for the hadron with enough phase space, something like a few hundred MEF, a few tens of MEF. And then you multiply that by this factor, you would conclude isospin breaking decay width would be some keV, or at most 100 keV, this kind of region. So 20 MEF width would lead you to conclude that decay must conserve isospin symmetry. Yeah, maybe we can make a break, yes. Question, if you have, you can still ask. Any questions? So if not, then let's just continue with more examples. Example of the use of heavy anti-quark diquark symmetry. Okay. So as I just said, so we for doubly heavy baryon, this can be connected to singly anti-heavy meson by using this kind of symmetry, right? And then this means if your doubly heavy baryon mass is, okay, this is cascade QQ, right? Its mass is given by the mass of the doubly heavy or the doubly heavy diquark plus some parameter of the dimension of the mass dimension, and then this one, the mass would be this. I would call this Q bar Q. This meson would be MQ plus the sim parameter up to corrections, up to relative corrections, 1 plus order LAMQCD over the approximation that we made, treating these two heavy quarks as a point-like particle, right? MQ over VQ, okay? So because basically the very gross feature of the non-perturbative interaction, they should be the same. But there are some corrections because this is a point-like particle, but these two are not really point-like. Well, these two, they have some distance. In a very heavy quark limit, they can become point-like. Okay? But there is certain approximation that introduces a certain level of uncertainty of this order. But then at least this tells you can have an estimate of the heavy diquark mass minus the heavy quark mass. It's approximately heavy or diquark baryon minus the heavy anti-heavy meson, right? So around this. But then, if we consider the anti-heavy baryon, okay, light baryon, we replace this heavy anti-quark by two heavy quarks. If the same approximation can be used, okay, then we would be able to predict, for instance, here, the mass would be M, doubly heavy, the heavy diquark, plus some B parameter, because now this B contains two light quarks. They should be larger than this A, right? And then here, it's the same heavy quark mass plus sim B up to this kind of corrections. 1 plus lambda order LAMQCD over MQ VQ. Now we have, this is a TQQ tetraquark, doubly heavy tetraquark. Doubly heavy tetraquark. This mass minus this singly heavy baryon, for instance, sigma C or lambda, sigma Q, lambda Q, okay, would be approximately the same as this one, right? And in this way, if you know all these different masses, you would be able to predict the doubly heavy tetraquark mass. And then this gives you access to the prediction of doubly heavy tetraquark TQQ masses. Of course, so far there's only a single doubly heavy baryon has been observed. You know which one? There is a cascade CC, doubly heavy baryon, cascade CC, right? 3620. Observed by RCB. Of course, it's, more than 20 years ago, there were also observations, reported observations by SELEX collaboration. They reported a mass of 3.52 Jeff. The third one, you mean this one? This one? This one is a CC. CCU, for instance, and then this will be carries two electric charges, 2 units of electric charge. Okay? For instance, this CCU, That will be cascade CC 3620. And okay, I skip the CX one because that one most people do not believe. Okay, that mass is also much smaller than this one. Here, the mass is 3.62 Jeff for the W Cham baryon. And then, of course, you can use this to make some prediction for the W Cham tetrahedral quark. But then the problem is that for that guy, the Cham quark might not be heavy enough. And then you would get something like this W Cham tetrahedral quark mass would be around this the threshold of a Cham meson and anti-Cham meson. And then this makes your approximation that your two heavy quarks are close to each other not valid anymore. But for the double bottom, although there were any observation of double bottom baryon, but there was some kind of quark model prediction by different groups, and S.D. Ashton, and Chris Crick, all these famous physicists, in 2017. They used some double bottom baryon masses predicted by Maria Kalena in his paper to predict the double bottom tetrahedral quark. Okay, that's one model input for the double bottom baryon. But once this is known, they could predict the double bottom tetrahedral quark. And it turns out that the predicted double bottom tetrahedral quark mass is smaller than the threshold of a pair of bottom mesons, TBB, with quantum numbers JP equals to 1 plus. The mass is approximately MB plus MB star minus, I cannot remember exactly the exact number, something around 100 MeV. And then this means this guy, if this exists, it can only decay weakly. It cannot decay through strong interaction. It cannot decay through electromagnetic interaction. It can only decay via weak interaction. And then this becomes a stable particle in the sense of a strong interaction, right? And of course, they are not the earliest group predicting the existence of a stable double bottom tetrahedral quark. Before that, many years ago, in 1980s or 1990s, there were already theoretical prediction, but they make explicit use of this heavy quark diquark symmetry argument. That's why I talk about their work here. Of course, in their prediction, they consider more fine structures. For instance, they consider the hyperfine splittings as just like the example I talked yesterday about the hyperfine splitting between d sub s 0, 2317, and d sub s 1, 2460. Using the same or similar consideration, you should be able to predict or consider the hyperfine splittings for the double bottom or doubly heavy tetrahedral quarks. And then you can make more fine predictions of their masses. But this, so far so good, looks very reasonable. But is there any loophole, right, for this consideration? Okay. It looks all very reasonable, right? But there is a loophole. The loophole is here. This light quark, they must be in color triplet, right? Color triplet. Color 3 in the color triplet representation. But now, you have two quarks, two light quarks, okay? Or two light anti-quarks. It's not necessarily that these two light quarks should be in color triplet, right? Color anti-triplet. They can be, or if I write in this way, okay, I think I just put Q bar. And then their color representations are color triplet or color anti-sextet. There is another possibility. So the two light quarks they can be in a different orientation. If this happens, then these two heavy quarks, they should also be in color sextet, right? And then this will release this one in color sextet, and then this release the QQ in color anti-triplet. Okay. So it's not guaranteed that doubly heavy tera quarks can be related to a singly heavy baryon. Excellent point. And then the executes would be the sextet, the sextet between the QQ through a one-gluon exchange. This gives you repulsion. And then the anti-triplet or triplet for anti-triplet for this QQ, this gives you attraction. And in the ground state, one hopes that in the ground state, the anti-triplet is dominating over the sextet. And in that way, then you can get back. But there are some quark model prediction shows that even for double bottom, seems to be the color sextet still plays a kind of sizable role. But only when you neglect this kind of configuration, and then you can establish this. Yeah. Okay, please, first. Yeah, I think so. Yeah, but I think why this could still be valid as this was later confirmed by there are many lattice QCD calculations leading to similar masses. Could be the ground state still you have this remaining in the anti-triplet, please. Excellent, of course. If you have, in principle, you can also have these molecular components, right? So you have, for instance, you can have Q bar, and Q bar. If you have this, and then this pair, they are far away from each other. In that way, you don't have this relation anymore, right? This would be the case for TCC. Right? For TCC, because TCC 3875 is so close to DD star threshold. And then this means its wave function, the DD star components inside its wave function is very far away from each other. This is from uncertainty principle, you know that. But for double bottom, for the double bottom case, if the mass of this guy is indeed 100 MeV below the BB star threshold, and then their distance becomes small. And in that way, it could still be reasonable to assume these two heavy quarks are close to each other. Okay. Indeed, this system is not that trivial, but there are more and more lattice QCD results for the double bottom tera quarks. They consistently agree with each other or each another that the ground state, the 1 plus BB, UD, U bar, D bar, this kind of double bottom tera quarks, their masses are below BB star thresholds by at least several tens of MeV. Okay, more questions? Please. Sorry, can you repeat? I don't know. Honestly speaking, I don't really know. So for the color triplet and color sextet, I think everything now you have 4-body system, right? All the colors they play a role. So in case that you have repulsive interaction for the sextet here, and then this could be to some extent saved by the interaction from other quarks. Okay. So Then let's come to the mostly discussed systems. The X372, right? The X3872. Okay. So that is a charmonium-like state. Charmonium-like state that was observed or discovered in deep psi pi plus pi minus final state at Bell experiment in 2003. Okay, so this year is really a year of hadron physics because many observations were made in the same year. I think there is a reason, right? The reason is that the B factories started to taking data a few years before that, and then they have collected many data, and then that year they reported many observations. So the most important property of this one, or the most weird property, is that the mass of the X372 is almost equal to the mass of D0 and the mass of D star 0, okay? Or I put bar on one of them. And the mass is smaller than quark model prediction for 1 plus plus, charmonium for 2p 1 plus plus by several tens math. Okay, I should see the quantum numbers of this one. The GPC equals to 1 plus plus. Okay, that was only determined in 2013 by LHCb. So this one, of course, this was after this observation, many models were proposed. And many people believe this guy should be isoscalar state. Of course, there are some complications which I will not go into details. That is, I cannot explain within this lecture. So for now, assume this is isoscalar because no charge partners have been found. Okay. Okay, if you want to know these details about this complication, you can talk to the teaching assistant because she recently did some very good analysis of this system. Okay, and then let me for now just assume this X that since there is no charge partners observed, then it's basically isoscalar state. And then the question is whether this decay is natural or not, right? For X decay into G psi pi plus pi minus. Okay? Whether this one should happen, because it happened, right? It happened. Or there is an exercise for you to consider. If you see this pi plus pi minus in this decay, it must be isospin vector state. Okay, you can see the exact description of the exercise in the afternoon. So this one must be isospin vector. Okay, and then this X can also decay into pi plus pi minus pi naught. Okay. And this one isospin scalar. At least from the G parity that I just talked about this or reviewed this morning, you see the G parity of pion is negative. Okay? Because the C parity of the pi 0 is positive, and then the isospin of pi is 1, And then Z parity is minus 1 to the power 1 times C parity is negative. And then these 2 pions has opposite Z parity compared to 3 pion. Okay? This means these 2 final states, they must have different isospin because C parity is always conserved. These have opposite or different isospin. Isospins. Right? So one of these decay must break isospin symmetry. So isospin symmetry breaking should happen or happens very sizably or significantly. That is because the measured value for this one, the branching fraction or partial width, is of order 1. But I just said, I think I already erased here. So the isospin breaking over isospin conserving decays should be suppressed by 3 to 4 orders magnitude. But here it's basically 1. Okay? So the very important reason for this is these 2 decays, they have very different phase spaces. That's because for this one, it mainly comes from rho 0. This one mainly comes from omega. And then your XA72 is located here, 3.7872 Jeff. And your deep side mass plus omega mass, how large is omega mass? You know, 782 Jeff, math, right? And deep side mass, 3097, right? You just sum up them. You find it's here. It's above the X72 mass. But how could this still happen? That's because the omega has a width of around 8 math, right? And then this means actually the mass for the resonance is not given value, right? It's always a distribution because its mass is not fixed. It's a resonance. It's a distribution. And then this distribution of deep side and omega has a tail which extends to below this X72 mass. And this X72 decays through the tail of the omega distribution. That's why its phase space becomes really small, but still it can still be happening. But on the other hand, the rho mass, 775 math, right? It's around here, but a little bit lower. But the very big difference is the rho width. How large is that? It's around 150 math, right? So this is also a distribution, but much broader distribution. And then this has much larger tail. And then this allows you to have much larger phase space for deep side pi or deep side rho compared to deep side omega. And then this huge difference in phase space gives you a very huge enhancement to the isospin breaking. Okay. I forgot to mention this XA72 now in the review of particle physics by particle data group. It's also known, aka as chi sub C1 3872. But this name does not mean particle data group regard this as a harmonium state. This only means it's a state having this quantum number chi C, chi Cj, means GPC equals to G plus plus, and isoscalar, right? But this does not mean PDG regards this as a CC bar state, okay? It's only a name for in the harmonium mass region. So that's That's the XA72. Of course, after this was discovered, many people appeared discussing what this really is. And then many of them, they would predict the existence of its bottom partner, right? You would think in any kind of model, does not really matter whether tetraquark model or Hadron molecular model, there should exist kind of partner of the X72 by just replacing CC bar pair by BB bar pair. And then you would get XB. Okay? And then CMS and Atlas, they search for this XB in epsilon, pi plus, pi minus, searched for XB or in this final state, and then they failed. No signal. But does this mean XB does not exist? No, right? What is the reason? Is this a good channel to search for XB? It is not. Right? So the analog to the charmonium sector is not that direct. You cannot simply replace deep psi by epsilon because they have a very subtle difference, and the subtle difference is important. The subtle difference is that for the XB, no matter what kind of model, okay, they generally predicts a mass below B star and B threshold by some tens math, by tens of math. Okay. It does not matter whether this is a tetraquark or Hadron molecular state, but at least there is kind of a difference between bottom sector and the charm sector. Here, although I already explained a large part of isospin breaking, but there is still remaining part of isospin breaking, which is still significant or sizable. That part can come from the D and D, the D and D star. It could be related to D star dynamics. But there, you have the D star plus mass minus D star 0 mass. It's around 3-4 math. It's around 4 math. Okay? And D star, D plus mass minus D 0 mass is also around 4 math. What are the sources of this mass difference? Right? There's also isospin breaking because D plus D 0, they are in the same isospin multiplate, right? The mass difference has the same reason as this part that I just erased. The up and down quark mass difference and vertical photons, right? So MD star, MD plus minus MD 0, it contains MD star, MD plus minus MD 0 from QCD. And I simply write, okay, MD plus minus MD 0 from QED. Okay? From QCD, that's U up and down quark mass difference. But here, that's from up and down charge difference. But now, if we move to the bottom sector, this part will be similar. Okay, MB plus minus MB 0, QCD. This part will be similar. Will be of similar order. Okay, because the only difference is up and down quark masses. But this one has a different sign. That is because B0, QED. these two have different signs. How should I write? 1 and 2. 1 and 2 have opposite signs. Qualitatively, we can conclude this because the bottom quark has different electric charge sign compared to the charm quark, right? So their QED contribution, they have different signs. This leads to different interference, right? And then here you have a constructive interference. Here you have destructive interference. And consequently, this one is around 4 MeV, but this one is less than 0.4 MeV. Okay, only around 0.36 MeV. I don't know whether this value has been updated, but from several years ago, if I use this, the masses at that time, so it should be around 0.3, 0.4 MeV. So it's much smaller than here. So this source of iso spin breaking is negligible, right? This means you do not have a good reason to have a sizable iso spin breaking here. On the other hand, here, I already explained a large part of iso spin breaking for the X comes from the phase space difference. But now, the epsilon plus epsilon mass plus rho mass and epsilon mass plus omega mass. How large is the epsilon mass? Yes? Yes, you're around 10 Jeff. Now I want a more accurate number, right? Because I want to make a comparison. I cannot remember. It's 9.46 or 9. I think 9.46. Jeff, you can check. It's around this value, if I remember correctly. So you plus this mass, around 0.8, right? Then sum up them. You would be able to get something like or 77, some 10.32, Jeff. But the B star plus B mass is around 5.28, 5.32, 10.6, Jeff. Okay, it's very different from here. That's why I care about this several hundred MeV, because here I want to be sure there is a several hundred MeV difference in the thresholds, and then this means the phase space difference between epsilon rho and epsilon omega is negligible for the decay of this guy, because the mass is, although you predict this XB does not matter what kind of model you assume, is a few tens MeV below this one, and then the phase space difference is still negligible, right? So for the XB decays into epsilon pi plus pi minus, the partial width should be much smaller than the partial width of the X3072 into deep psi pi plus pi minus, because this is iso spin breaking. Okay. So that means the CMS and Atlas, they search for the XB in the iso spin breaking channel. For sure, you cannot find it, right? It's because you have a huge iso spin breaking here, iso spin breaking suppression. And then they could search for this in epsilon 3 pi, for instance. But then that is not easy. Then better channel would be epsilon plus 3 pi, when pi plus pi minus pi naught, or chi bj plus photon, something like this, right? But this pi naught decays into 2 photons. So this will involve final states with photons, which is then more challenging for LC experiments, right? So that's for the X72. And then there is the ZC 3900 plus minus decays into deep psi pi plus minus reported by Best 3 Baer in 2013. And then also decays into D star bar plus minus reported by Best 3 either 2013 or 2014. Okay. Here the mass is also similar to the threshold of D star D. Okay. And then there are ZC 4020 decays into HC pi plus pi minus, and also decays into D star bar pi plus pi minus, reported at Best 3. And the mass of this one is around D star, twice D star masses. And earlier than that, there is ZB 10610 plus minus. This decays into upsilon 1s, 2s, 3s, pi plus pi minus, or HB 1p, 2p, pi plus pi minus, and also ZB 10650 decays into the same final states. And then later, signals also were found in B bar B final states for this one, and B star bar, but with less statistical significance for this one. Okay, Baer, 2011. Okay. And then you see all of them, including the XA72, they are close to the thresholds of a pair of heavy mesons. And then there are many theoretical papers proposing they could be related to, they could be hadron molecules. Okay, I do not judge here whether they are hadron molecules or not, because there are many very dedicated studies for that. But at least this motivates us to study the interaction between a pair of hadrons, right? Interactions between heavy hadron pair, heavy meson pair. What do I mean by this? I want to study the S-wave interaction. Okay? Because all these are close to these thresholds, and they couple strongly in S-wave to these final states. This is evidently seen from the branching fraction that you would see from the the experimental observation. That although the XA72 is so close to DD star threshold, but it still has very large branching fraction to DD star. This already tells you it has very strong channel coupling to DD star. Okay? Now, I want to study the interaction between this heavy meson pair. Now I write these heavy mesons, D star. I call them as capital H because D and D star, they are in the same spin multiplet, right? I call them together as capital H. Okay. This spin multiplet, the total angular momentum of the light quarks, light degrees of freedom, is what? 1/2. Parity is minus, right? Now I want to make use of this. Okay, and then their anti-particles are d bar, d star bar. Of course, they are also SL P equal to 1/2 minus, right? So they are just antiparticles. It's just this one refers to the light antiquarks. Here it refers to the light quark inside this. Right? Now, I want to see what we can conclude from this consideration. We consider all possible charm meson, anti-charm meson pairs in S-wave. We write down all of them. We see how many possibilities we could have. And then we have D bar, right? We have D bar. And then in S-wave, the total angular momentum D bar system in S-wave should be 0, right? Because they are spin 0 particles. There is no orbital angular momentum, and the total angular momentum will be 0. Now it's G. It's total angular momentum. You see, now I write this as a G, which is different from this one. This one refers to the angular momentum of the light degrees of freedom. This capital G refers to the spin or angular momentum of the whole system, including light quarks and heavy quarks. Okay? And the parity, P. What is the parity for S with DD bar? Is the parity positive or negative? Positive, yes. Because for parity, a pair of meson and anti-meson is -1 to the power L, right? Because they are bosons. The particle and anti-particle, the boson, anti-boson, or boson and its antiparticle, they share the same parity. Okay. And the C parity. What is the C parity of this one? C equals to what? -1 to the power L plus S. Although I derived this for fermion anti-fermion system, but I also commented that the formula also holds for boson anti-boson, right? Because for boson anti-boson, you don't have this -1 to the power 1 for parity, and then you don't have you also don't have this -1 factor for the spin, and then you just secure both of them. You still have -1 to power L plus S. Okay, and then the L we have is S wave. L equals to 0. Okay? L equal to 0. That's for S wave. Total spin. They don't have any spin. The total spin is again 0, right? And then, of course, we have 0 plus plus. But now, if we consider D star bar, okay? Because the C parity is a good quantum number of QCD, and then this means all the flavor neutral system in QCD as Hamiltonian eigenstates must have a given C parity, right? It must be C parity eigenstate. So this single pair cannot satisfy that requirement. It must plus or minus its charge conjugation, right? Only in this way you can form C parity eigenstates. But I said yesterday, for D meson, this kind of meson, this is not flavor neutral. It's not C eigenstate, right? Eigenstate. This means we can the C parity is not given for sure. We can choose the C parity, or I write in this way. I don't write using operators. I simply write in this way. Okay, make a C parity transformation. We can choose this to be either positive or negative. It's up to our choice, right? Because they are not isospin they are not C parity eigenstates. So they don't have any given eigenvalue. We can choose this is our Fisk convention. So we will choose the Fisk convention that D under charge conjugation becomes plus D bar, and D star and the charge conjugation becomes minus D star bar. Okay, this is the convention used in many papers. They choose this kind of convention because the pi 0 has a positive C parity and the rho 0 has negative C parity. But this is completely up to your choice. You can choose any phases here, anything you can choose, any sign you can choose. As long as you use consistent phase convention, all the physical observables do not depend on your choice. Okay? All these different signs will cancel at the end. Now we simply choose this one. Okay, this one means I use this part. This one means this D star bar and the charge conjugation will becomes D bar, right? I choose positive sign here, negative sign here, minus D star, right? So this means under charge conjugation, this pair becomes this pair, has a minus sign in front of them. And then we can write this as, sorry, if this is negative sign, D bar, oh, sorry, D star. And then this means this pair should have what kind of C parity? Positive, right? Because under charge conjugation, this introduces a negative sign. This introduces another negative sign. This negative sign, it just tells you this has a positive C parity. Positive C parity. And if we consider S wave, and then the total spin is 1, spin 0, spin 1, and then you get total spin 1. S wave, positive parity, right? We have this. And then, of course, if we normalize that, then we put 1 over square root 2. And then we have another pair, D star bar plus D bar, D star, okay? This one, what is the quantum number of this one? 1, what? What's the parity? Plus, right, C parity. Positive or negative? Negative, right? Because your C parity transformation, this one and the C parity becomes minus D bar, D star, minus D star bar, right? Which is an opposite sign compared to the above one. And then we have one more possible meson pairs, D star bar, right? But D star has a spin 1. Okay, we have 2 spin 1 particles. Spin 1, spin 1. We can have the total spin. We have 3 possibilities: 0, 1, and 2. Right? We have 3 different possibilities, and then this means we can have D star bar with spin 0 and also positive parity. But of course, now we want to decide on the C parity. Okay. Now again, it's particle and it's antiparticle. The C parity is given by minus 1 to the power L plus S, right? L plus S. L for S wave, L equals to 0. S is total spin. If the total angular momentum is 0, this means the total spin of this star is also 0, right? L is 0, S is 0, and the L plus S is an even number. And then, of course, this means this pair should have positive C parity. That's why I put it in this line, okay? And then we have we have 2 plus plus, right? The 2 plus plus, this star bar. The difference compared to the 0 plus plus is only the total spin, right? But the total spin, this one is 0, this one is 2. Both are even number, and then the C parity should be the same. That's why here we have 2 plus plus. How about the spin 1 combination? What is the C parity of the spin 1 D star bar? Minus, exactly. D star bar, right? The C parity is minus, okay? So now we have 1, 2, 3, 4, 5, 6. 6 pairs of this charm meson, anti-charm meson. For each isospin, because so far I have not put any isospin. 6 pairs, 6 pairs for each isospin. The total isospin can be either 0 or 1, right? Because the isospin of D and D star is 1/2. And the total isospin can be either 0 or 1. So in total, we would have 12 pairs of charm meson, anti-charm meson. And then we will see these 12 pairs, actually they can be grouped into 4 different multiplets. Okay. Yeah, maybe we go to that point tomorrow, the day after tomorrow. Okay, good. Questions, please. Yes. Yes. Well, two reasons. First, the phase space. The phase space for this one, both the phase spaces of these 2 channels are similar for the XB, because the XB mass is generally expected to be higher than these thresholds by 200 MeV or so, or even higher, even more. So there is really their width would not play a big role compared to the already available 200 MeV phase space. But for the XA72, the phase space difference is huge, because the XA72 mass is almost the same as dipside rho threshold, and even below the dipside omega threshold, nominal threshold, if you just simply use the central values of their masses. So there's a huge difference. More questions? So if not, then so today this afternoon, my teaching assistants they will show you the exercises probably on the screen, and then you can think of that. Tomorrow, she or he or them, they can or you can discuss. You can ask any question to them, and then they can solve the problems if you cannot solve. And on Thursday, actually, I want to change a little bit the schedule, because my flight is in the afternoon. So probably it's better for me to talk the first 2 hours on Thursday morning, and then after my lectures, I need to leave. Okay. Thank you. Good.